or when the equilibrium is established, the point is the same relationship will hold like we did for this one. Okay, so that's for a very strong acid will go almost forward. It's not going to come back easily. So that one you have a small, but a weak acid or weak base will go back and forth. And the weak acid or weak base, we said, is a good buffer system. So that when you add small acid, it will take it. If you add small base, it will take it. Then that system is called buffer system. Okay, right? That will be for weak bases and weak acid with their corresponding whatever salt. Okay, or the dissociated part component. So the weak base with the dissociated component will form the buffer system. All right. Okay, so from there we move to the Gibbs free energy, and that was the last thing we talked about. Okay, so this Gibbs free energy is telling us how a reaction will be spontaneous or not be spontaneous. Okay, and it's the component the same as the work done in the system, the energy that is available for work to be done. Okay, so the same equilibrium system, once the equilibrium has been established, if the equilibrium has been established, then of course you'll be able to get through the system, right? So that brings us to the end of this section. The next one we're going to look at reactions, redox reactions, simple reactions to redox reactions, and so on, right? Now we talked about so we are looking at reactions, okay? Remember, always construct the table. Helium, like beating, boys come near ours, nine, Maggie, always silly, people send, calling, cargo, Kwame, Charles. Okay? So always try to find the names to get the first 20 minutes when it comes to reactions. Okay? Okay, at the end of the 20, we have 10 transition metals following. Okay, right, so this is period 1, period 2, period 3, period 4. So, okay, and this is what group 1, group 2, group 3, group 4, group 5, group 6, group 7, group 8. But this is the old system. It's the old system. So this is rather 18. We have 17, 16, 15, 14, 13. Okay? Right. Alright, so that is how always get your periodic table. The modern periodic table, of course. Right, which depends on the atomic number. Okay. So the normal reaction, we said, for instance, if I have aluminum chloride. Okay, so aluminum chloride, how do I get it? This plus 3, this minus 1. So I just need to put the two together. So Al, this 1, this 3. Okay, 1 is not written, so this is my reaction. Now I'm reacting it with, let's say, magnesium hydroxide. Okay, magnesium is 2 plus, oxide is minus 1. Okay, you must note them. Sulfate 2 minus, nitrate 1 minus, carbonate 2 minus. Alright, so you must, and then phosphate is your 3 minus. Okay, so you must always look at that, so that you can. But these ones you need to move them off, and as you work with them more, it will stay so better. So here I'm just going to cross multiply. This is going to be 1. This is into bracket. I'm going to put 2 here. Okay, so 1 is not written, so there is it. So if I'm reacting this with that, let's see what happens. The positive must react with what? The negative. Negative must react with the positive. So this. So Al is going to react with hydroxide. It's going to get aluminum hydroxide. Let's see how that will go. When you are putting them together, the same principle. This is what? Plus 3, this is minus 2, just cross them. So here will be 2, here will be 3. So this is 1, this is minus 1. So here will be what? 1, and here will be 3. Okay, 1 is not written, so now let's react chloride and magnesium. So I have magnesium, chloride. Magnesium is 2 plus, chloride is minus 1. So I just cross them, 1 here, 2 here. Okay? So when you finish, you clean this one. So when you have formed them like that, the next thing is to come and make sure that the atoms, elements balance on each side of the equation. Okay, so aluminium, we have 1 here. Aluminium, how many do you have here? 1, that's okay. Chloride, we have how many? 3 here. How many do you have here? 2. So how can you make this one 3? So we must find a way to make it 3. Okay, so let's see how, maybe when we go on, we'll get it. Now let's see, Mg, we have 1 here, we have 1 there. OH, we have 2 here. We have how many here? 3. So how do you make it? So let's see, if you have 3, from here, chloride, 3, you want to make it 2. You should multiply this by what? 3, 2 over 3. That means if you multiply here by 2 over 3, that is how it's going to go. It's going to give you what? This is going to cancel 8, and then give you 2 here. If you multiply here by 2 over 3, this would have been converted. So here is 1. How do you get your 1 here too? So you see that what you do is you do trial and error method for the simplicity of the equation that you're going to do. I will not go on now. So you do your trial and error method. You try to see which one you balance to get the equation. So you keep on trying in that order until you come up with the final. So how do you get it? Let's see. We have 3 here and then we have 2 here. So that, if you are dealing with fractions, it will make it very difficult for you to get an answer. So you go in the whole numbers, okay? So if you have 3 here and you have 2 here, what you do is that you find a common factor for the 2. That means if you multiply this by this, what you get, make sure each side has that. So 3 times 2 is 6. So I must make sure this side will get to 6. For this one to get to 6, I must multiply here by 2. If I multiply here by 2, what will this become? It will become 6. But here is 2. How can it become 6? Unless I put 3 here. Okay? Good. So when I put 3 there, let's see. Now this 2 has changed aluminium to what? 2. But aluminium, we have 1 here. So how can I make aluminium 2 here? I have to put 2 here. So it's trial and error until you get the answer. So when I put 2 here, aluminium is now 2. So I've satisfied this and that. Okay, now let's go to Mg. Mg is 1 here. Now Mg has become 3. How do I make Mg 3 here? I have to multiply here by 3. Okay? Now if I multiply here by 3, Mg has balance. Now let's see whether OH will balance. OH 2 here, 3 here will make it 6. How many OH do you have here? 3 here, 2, so it's making 6. So you see that the equation now is balanced. So this is the balanced equation. Okay? Right, so this is the balanced equation. So first get your table and then go. So this is the simple balancing of equation approach. Okay? So this is simple. So in this case, the ions, these are ionic reactions, okay? The ions are there, they are fixed states, okay? That means if it's magnesium is 2 plus, it's almost all the time 2 plus, okay? If aluminium is 3 plus, it's almost all the time 3 plus, okay? Same thing throughout. Okay, now let's look at the next step we call redox reaction. In fact, what I want us to take, the concept is the redox reaction is no different from this. The only factor that comes to play is that the states, the various elements that we'll be dealing with, they can exist in different states, especially the transition elements. Because we said transition element, they can exist in the D and S, the S, the 4, the 4S, and then the 3D orbits. They are close, so the electrons can go back and forth to be in state plus 3 or plus 2. For instance, iron can be 2 plus, or iron can be 3 plus. Okay, so which one will be in the reaction? So that means we will need a way to balance that one. That is where we will be going to the redox reaction. Okay, so this is a simple balancing of the equation. So with this, we have balanced the equation. Good. Now let's look at. Let me put it down. This is what? Plus 3, okay? MgCl2. Okay, let me put it there. So that you see it going. Okay? So that is the end of the simple equation, balancing equation. We're going to use the same principle, just add some few bits to it in the redox reaction. Okay, so let's go. Now, before we go on, I always want to introduce briefly the part of organic chemistry. Organic chemistry means the part of the chemistry that deals with carbon and carbon compounds, okay? With the section of maybe carbon dioxide and then CO3, okay? CO3 2 minus, okay? The section of that, all other carbon containing compounds will be put under the carbon, the organic chemistry. So when you say organic, always start thinking about carbon and then its related compounds. The section of CO2 and then CO3 2 minus, right? Okay, so at this point, I said I'll add something. We can have some organic compounds like this COH, okay? This is representing a lot of carbons. R represents a lot. So this is actually C combined with, okay, this and this. So this one is the OH. It can lose this one to become this minus. So it means this is like this one minus 1 and this plus 1. Okay, so it is going to react with this one or with each class. Something like that. So just get that picture. Okay, so this is one of the. It's just like we have the sulfate 4. 2 minus. Okay. This is okay. If it is alcohol is written as this. Okay. Right. So this one can also become. Let me make it this way. Minus something like that. Okay. This can also take up like that to react in a reaction. Okay. So you can look at it in that sense. So they also have charges like this ones have charges. You have minus 1 with it hydrogen ion as plus 1. This one is CO. So this alkanoic acid. This is alkanol or the alcohol group. Okay. Just briefly, we'll come to it when we get to organic chemistry. Let's go to the reverse reaction. So the redox reaction is simply reducing. So we have the reducing part of the reaction, and then we have oxidation part of the reaction. Okay. Okay. So the reaction that is coming together, which involves, let's say, X plus electrons. Okay. If we are adding, if the reaction is such that this and that are adding, that is, we are talking with respect to the reaction. So not the product, the reaction is going on to form a product. So if that process is adding electrons, then that is what a reducing reaction. Okay. If the process is such that this is losing electrons, it is becoming this. It's losing electrons. So it is losing, the process is losing. Okay, this one was reacting. Okay, reacting with this, it is reducing. That means P was reducing. If it is releasing, okay, it is breaking down to release electrons. Okay, to release electrons, then this is what oxidation reaction. Okay, so this is how the process will be. Now, any process, anything that will help to reduce, anything that will help to reduce. To help this reaction to go on, it's a reducing agent. So I'm just making things easier. It's a reducing agent. And anything that will help to take electrons away, that will help to take electrons away, okay, will be an oxidizing agent. Okay, so it's more, it takes electrons. It takes your electron. So it enables you to release your electrons, okay, and then that is an oxidizing agent. So a reducing agent will help to add electrons to you. Okay, right. So that is basically the principle. Once you get this, now if you look at it, if you lose electrons, it becomes what? Positive. So you see that in terms of oxidation, the element involved increases in charge. But here, if it was, let's say, 2+, it will become what? one plus after receiving one electron. So see that here there's reduction in the state in the charge. Okay, so there's reduction in the charge. That is reducing part. At oxidation, so the oxidation there's increase in charge, electrons are released, are given away. Okay, and an agent helps to give away the electrons. In reduction, electrons are accepted, charge reduced, and then an agent helps the process to go on. Okay, so three things. Okay, what happens to the electrons? Okay, the charges. Okay, and then the third, the agents. If you look at it this way, you're always able to see and be able to tell what type of reaction is going on. Okay, so this is how it is. Okay, so the reaction, the type of reaction, if it is reducing, if electron is reduced, electron is negative, so if it adds to you, it will reduce your charge. So if it's a reducing incident, then it's a reduction, the reduction is a reaction. If it's giving away electrons, okay, if it is giving away electrons, okay, as the reaction is going on to give away electrons, then it is what? Oxidation. Okay, right. So if something helps you to take away your electrons, so you always look at the reaction, not the product. Okay, the reaction part, the process happening. Then, because they are asking what is the reaction, not what is the product. What reaction is going on? Okay, so where the reaction is focused on, and look at the process to see whether it is a reducing reaction, it's a reduction reaction, or oxidation reaction. Right. So, having gone through the basics, let's look at some of these equations. We can balance them. So let's say we have zinc reacting with copper, and then we want to see how it will go. Now let's assume that zinc is able to release, let's say 2 grams, okay, it's able to release electrons into copper. Okay, now we are using these two because they have various they can have various charges, so they fall under redox reaction. So what you do is you always write the equation in two halves. You can write the oxidation half, then you can write the reduction half. Okay, so let's look at it. Now let's take our zinc. What will happen is we'll first write zinc. Zinc is now is going to release electrons to this one. It is going to reduce this one. Okay. But on this side, no, this is reducing and this is accepting. So this part, this whole reaction is a redox reaction. But the half equation, let's see which one will be redox, which one will be green. So here zinc is going to be what? Zinc is going to lose 2, so it's going to lose 2 electrons, so it will become 2 plus what? 2E. This equation 1, 2 electrons, okay? Now copper, what is copper going to do? Copper 2 plus is going to accept electrons, so it's going to accept whatever electrons is coming, 2 electrons, to become, so this 2 is going to neutralize it and it will become 0, but we don't put 0, so it's that. So this equation 2. So you see that this part of the reaction is what? Oxidation. It is just reducing. This is the reaction. It's reducing. Now this is taking. This is the reaction. It is what? Releasing. So it is oxidation. Okay. This is the part of the reaction. It's accepting electrons. So it is being reduced. So this is the reduction. This kind of reaction going on is reducing reaction. So it's the reduction part. It becomes this. Right. Now, so when you have done this, the first half. This is the second half. Okay. When you have done that, you add them together. You put the two together. Okay. So we have zinc plus copper 2 plus 2E copper plus zinc 2 plus 2E. Okay. So this is how the reaction is going to be. Now check whether everything is balanced. Zinc is 1, zinc is 1 here. Copper is 1, copper is 1 here. When you finish, then you come to the charges. When you are balancing the charges, make sure the charges here must be equal to this. What is the total charge here? This plus 2, this minus 2, so it is 0. this is plus 2, this is minus 2, so it's 0. So it means the charges are okay. So you don't need to add. You use electrons to balance the charge, so you don't need to add or subtract any charge. So this cancels out. And the equation becomes the same. Since when you are writing the equation, you don't bring electrons, you take off the electrons. When you have balanced the equation. Okay, so this is it. Right, so this is a redox reaction, a simple redox reaction. We'll go in steps, then get to where we move into. Right, so at this point, let's look at something. Now this going to that can have a certain voltage, okay? Let's say it is plus 3, assuming, okay? And then this accepting, so it means this has a very good, it's positive. When it's positive, it means it is going to, it's going on, that pathway is good. It's going to be spontaneous, or it's good, it should go down well, okay? Now let's say this other half of the reaction receiving is also positive, because it means it is, let's say, plus 2. Then it's also going to go downward, okay? Now this part is releasing electrons, and this is accepting. So if you have a system like this, okay, let's say this is my zinc, and this is my copper, okay? Let's say I have my copper 2 phosphate sulfate here in the solution. If I connect this with a wire, this is going to release electrons, okay? Okay, these 2 plugs. When it comes here, this is a solution. When the electrons get here, because this is 2 plus, this is copper 2 plus in the solution. This is a copper rod, okay? Copper 2 plus in the solution. It is going to accept the electrons. It will go there and accept, and then form copper on it. So you see that copper will be collecting on this one. Current is what flowing, and these charges are flowing that way. Okay, so this comes into solution, and this 2 plus. Okay, as this goes into solution, this goes here. So you see that the cations are also going, the positive ions are also moving. Okay, this is going and this is replacing it. Okay, this is going and this is replacing it. Once the electrons are also coming, so as the protons are moving this way, the electrons are also coming that way. Okay, so of course when electrons are coming this way, it is the same as a charge, positive charge is going that way, because that is what you say the conventional current is. Okay, the conventional current, which is positive moving, is moving in that direction. Okay, good. So at this point, you see that this becomes a cell, because it is in solution. That will be a wet kind of cell. Okay, wet kind of cell. Okay, so this will be a wet kind of cell. Now this will go on. If we work out the first equation, we said this one going on like that, the voltage is 3. This going on like that, the voltage is plus 2. Okay, it can be negative, but we are saying plus 2 plus 3. So at the end we're going to get what, plus 5. So it means for this cell, the voltage for this cell will be plus 5. Okay, if we turn the equation, it may not work, because maybe we get negative. If it's negative, it means it's not going to work. Right. So this will be wet, because we are dealing with a solution like that. Sometimes you have a salt bridge in here, okay, to help balance the kind of reaction going on. Okay, so that will be a wet cell. A dry cell will not have the solution. It may have a paste or a gel, but the arrangement is always, you have the rods there. Okay? Right. So the anode will be releasing the electrons. Okay, the cations will be catched at the cathode. Okay, depending on what you're looking at. Okay. Alright, so the simple way to remember is that we use the cathode ray tube. Okay, the cathode ray tube. What it did was, the cathode ray was shooting electrons. So it's shooting electrons. So the one that is shooting electrons becomes the cathode. Okay, that is one way to remember. So the one losing electrons, shooting the electrons, becomes the cathode. And then obviously the other one becomes what, the anode. Okay, becomes the anode. Alright. Now the arrangement of this is in solution, so it's wet. The arrangement of this zinc and copper is what you call the Daniel. It's in the Daniel cell. Okay. Then we have the Lefranchi cell. Lefranchi cell. So we have the wet and then we have a dry, okay? But that one uses zinc and then carbon rod, okay? So the zinc is shooting the electron, so it is the cathode, okay? The carbon is going to accept. Then we have the media. So if the medium has solution, that is the wet. If it has gel or jelly kind of solution, then that is the dry cell, okay? So electron we have two, the wet and dry, and the zinc and carbon. Then when it comes to Daniel, it is zinc and copper, okay? Then, but of course, to avoid short circuiting, remember that if this is our zinc, and let's say this container is copper, we will not let this one touch the zinc, other than that straight away there will be flow, very short flow, high flow. That will be short circuiting. Short circuiting usually converts most of the energy into heat, and then that is wasted. So we have to avoid short circuiting by either putting something to prevent the contact, okay? And then the medium also serves as a medium to accept the electrons, right? To kind of depolarize or accept the incoming flow of what do you call it, the charge. All right. So that is for cells, which will be discussed later. But I'm bringing it in because we have this kind of equation which fits the cell. That is what I described. Okay. So various cells together form battery. All right. So that is that for this basic redox reaction. We'll move on to the second kind of redox reaction. So take it, if you are sending electrons away, that's the cathode ray. That is the genesis of giving names. Cathode ray, in that experiment, the electrons were shot from the cathode part, okay? So if you are shooting electrons, you have the cathode, the one accepting the electrons, or that component becomes the anode, the anode, right? So that can help you to judge in both, in all different cells arrangement, okay? So we have the rechargeable cells too, the sulfuric acid kind of medium kind of cells too. The rechargeable, after the electrons have flown for a while, after the electrons have gone through the phases for a while, okay? The point is at the point the voltage falls, okay, or we have the battery dropping, you can recharge it, okay? So those that we can recharge are the rechargeable cells, okay, right, or battery, right, in that sense. So the car battery is, for instance, is rechargeable. Okay. All right, so that is I think that is what we can. Let me clean this part so that we move on to the second redox reaction. Now let's see how we can balance this one. So we are going to balance this redox reaction. Redox reaction because the charge here of sulfur is not the same as this. The charge of chromate is not this. Chromium is not the same as the chromium there. So since the charges are not the same, then we are dealing with redox reaction. And the question says we should do this reaction in an acidic medium. Okay, so like I said, it's the same principle like the simple balancing of the equation, but we have to make account for the charges by using electrons. And then where we have oxygen too, we balance the oxygen either using, if it is in acidic medium, we use H plus and water. If it is in basic medium, we use OH and then water, okay, to balance the oxygen aspect, okay. So let's put this one somewhere here. So first of all, we should write the half equations. So we should write the first half equation. Let's say S is going into what? Here S, what's the charge of S? This is plus 1, so it means it is plus 2 here, total plus 2. Therefore this must be minus 2. So it is minus 2 here, and then it came here, it became what? S, here is 0. Okay? So what do you think has happened? From 2 minus 2 to this, what has happened? It has what? It means its electrons have been lost. It has released electrons, so this is plus what? 2p here. Okay? You can put it that way. But this is losing electron. Sulfur has lost electrons to come to 0. So this kind of reaction, this is the oxidation. Here, electrons are being released, so this is the oxidation part. Okay? So let's balance it here. Let's see how it will go. Okay? Let's see whether it's balanced. S here. We have our 1S here. Okay? What about the H that we have? Because we said this is an acidic medium. You should remember that Now the first thing you must look at. So here what happens? Hydrogen 2 plus, we don't have hydrogen here. So what do? You must add, it's an acidic medium, so you must add H plus to where there's no hydrogen. So this becomes what? H. Sorry. S becoming what? S plus 2E plus H. How many H are there? 2 plus, okay? Good. Now, when you have done that, when you have balanced the atoms, always balance the atoms first. When you have balanced the atoms, H same here, same here, okay? So when you have balanced the atom, now check whether the electrons are balanced. In fact, we could have decided not to add this one, you could have just written this and that. And then when you balance the electrons, we balance the atoms, then we come to the electrons, okay? But since we are putting there, let's see how it will work out. Okay, so here is minus 2, here is plus 2, so the total charge on this side is 0, total charge here is also 0, so it means it is balanced for each one, the oxidation part. That's the oxidation part. Now let's look at the reduction part. It's chromate 2, 0, 7, okay, becoming chromate what, 2, 3 plus. Okay, here let's see the charge of the chromium here. What you do is you find the total charge here. That one, this is oxygen is what? Minus 2. So 7 times minus 2 becomes minus 14. Okay, so this the charge on total charge on oxygen is minus 14, but the total charge on these two is minus 2. So what charge should be on this to make this whole thing have minus 2 charge? Okay, this whole thing have minus 2 charge. Unless this one is what? 12. If this one is 12, it will make the whole thing minus 2. So this is how you do it. You do it that way. If this whole thing is 12, then it will make this one minus 2. Okay? But remember, this we have 2 of that. So if it's 12, it means half 6. Okay, so it means chromium is what? 6 here, plus 6 here. And it has become what? Plus 3 here. So from plus 6 to plus 3. What do you think is happening? We have accepted electrons to become plus 3. So electrons will be going to be added here. Okay? That gives you the picture. So it means this is going to be the reduction part of the reaction. So let's write it well. So let's balance the atoms first. Atoms. Here we have 2. Here we have what? 2. So that's balance. Okay? But oxygen we have 7 here, we don't have oxygen here. To balance the oxygen, we use what? Because it is acidic medium,